relationship, probably the most famous relationship in this field, which is mass metallicity relationship for star-forming galaxies. In the right corner, you can see the on the y-axis the metallicity, on the x-axis the logarithm of stellar mass. And here in this paper, Andrews and Martini 2013, they show, first of all, their own results, which are showing the tight correlation between the two quantities, and second of all, report different literature findings. So what has been found is that first of all, more massive galaxies are more metal enriched, but second of all, the less massive galaxies are even less massive than it would be predicted from just extending the strands down. So there's some more metal depletion, probably due to the shallower galactic gravitational potentials. Second of all, it has been studied that there is a certain cosmological evolution of this relationship. So at higher redshift, galaxies tend to be less enriched. And for singular objects, what people see is there are negative radial gradients, which are suggesting that the evolution happens from inside out. And so in general, the metallicity can give us a lot of bounds to the galaxy evolution theories and can tell a lot about star formation, gas inflows, and gas outflows. But as we know, AGNs are in general very influential for the galaxy evolution. Here I'm showing you this cartoon from Silk and Mammon illustrating this very famous plot, and it illustrates that the galaxy luminosity function, which we are getting from observations, here just plotted in blue or just sketched in blue, departs from predicted based on theory, here sketched in red. For the lower end of this luminosity end, excuse me, for the galaxies with the lower luminosities, it is usually explained through the star-forming activities and supernova activities. However, for the highest luminosity galaxies, some much more energetic processes are required, and we believe that the AGNs are the reason for this departure. So we know that in general, AGN are having a very important role in the galaxy evolution. But so what about the chemical evolution of the galaxies? There are multiple studies of, excuse me. There are multiple studies which are detailing the AGN galaxies' chemical evolution. However, there are much less of them. And here what you can see is the study from Thomas et al. 2019, in which they have probed the metallicity mass relationship for Seyfert galaxies and compared it to the star-forming one, which I showed you a few slides earlier. So what you can see here that the purple points are for the Seyferts. You can see that certain relation exists. However, there is more scatter in comparison to the star-forming one. Then there are a lot of spatially resolved optical studies. So for some of them, for instance, here in NGC 7130, Amiri et al. 2024 reported the positive radial gradient of metallicity, which can imply certain transport of metals from the nucleus, here on the top panel. And also in Aram et al. 2024, authors reported the positive radial metallicity profiles, which also anti-correlated with the Eddington ratios. On the other hand, different Seyfert galaxies are showing negative metallicity profiles. Here, there is an example of IC 5063 from Amiri et al. 2025. And also there are studies of manga dataset Seyfert galaxies in manga dataset, which show in general systematic under-enrichment in nuclear regions. And on the top of that, to make the picture even a bit more complicated, in different type of AGNs, quasars, the studies of the metallicity of the broadline regions are showing the high supersolar metallicities. So there are still a lot of questions on how and if AGN are influencing the chemical evolution of the galaxies. And what we wanted to do in this paper, we wanted to try to probe the metallicity with the highest possible spatial resolution in order to try to provide some new information and some new ideas and understanding. So what we done in our work is that we took the HST observation in narrowband filters, thanks to which we could probe the emission in O3, S2, H-alpha plus N2, and H-beta emission lines. We supplemented them with Muse data, which have slightly worse spatial resolution. However, they have a great spectral resolution, and which allowed us to get the estimates almost at slightly lower, but still on the very good spatial, with a very good spatial resolution estimate of ionization parameter, pressure, and H-alpha to N2 ratios. And then we applied the metallicity diagnostics based on those lines in order to create a map with a very high resolution of metallicity in Mrk 573. However, I mentioned that we've done it for the AGN type spectra. So at the beginning, we had to somehow distinguish between different parts of the galaxy. So in order to do that, we used optical diagnostic diagrams. In optical diagnostic diagrams, on the y-axis, we plot the logarithm of the O3 versus H-beta fluxes. And on the x-axis, it depends on the exact type. For VO diagrams, which we're using, we plot S2 versus H-alpha flux. And based on where the galaxies, or in our case, the regions of the galaxy, are situated in this plot, we can classify them as either Seyfert or AGN type, which are usually associated with the excitation based from the AGN radiation. Sometimes also these parts of the plot can be occupied by the excitation through fast shocks with precursors. Then there, on the right side of the plot, linear type of regions and galaxies are situated, which either can be the the exciting mechanism is either obscure AGN radiation or slower shock, or can be connected to the also stellar activity. And in left lower corner, the H2 type excitation, which is linked to star forming activity, is situated. And even though originally and very broadly, these diagrams are used to classify the whole galaxies, for instance, here in this plot, you can see the galaxies from SDSS. It is possible using both HST and Muse data to classify these different regions of the galaxies thanks to this plot. So these ratios can be calculated pixel by pixel, and then they can be just plotted on the diagram. We chose Mrk 573 because it is a galaxy which has been observed throughout the in different wavelengths and it has a very good quality data. It is a nearby Seyfert 2 galaxy. It is Compton-thick, which means that it's heavily obscured in X-rays. The nucleus is heavily obscured in X-rays. What means is that with Chandra, we can probe very well the extended emission. And here you can see the series of plots from Paggi et al. 2015. And in the left top corner, you see the X-ray emission in 0.322 kiloelectronvolts from Chandra. In the right top corner, you see the optical emission of O3, oxygen-free. And you can see this biconical structure, which in the left bottom panel is shown the contours of the optical emission O3, are plotted on the top of the X-rays. So you can see this biconical structure, which is traced by both of these. And then on the right side of this plot, you see also the radio contours from 6 centimeters, which you can see the enhancement of the soft X-rays where the lobes are. And so what we done is, first of all, we used the Muse data for the source. We derived the maps of, first of all, H-alpha to N2 ratios. And second of all, we used the diagnostics from Zhu et al. 2023 to derive the maps of the ionization parameters and pressure parameter. In general, the metallicity diagnostics should be only the values of those diagnostics mostly depend on metallicities, however, and are almost independent on ionization and pressures. However, still it's better to provide those measurements and to use them in order to make sure that we are getting the best possible results and the most detailed. Then we used HSD data to obtain maps in all three, S2, H alpha plus N2, and H beta. Then we constructed the VO diagram and map, and we also color-coded the maps, VO maps. So in general, here you can see in red the Seyfert type regions. The more darker the red is, the further away here it is from the division line between Seyfert and liners. So you can see here this biconical structure. And then on pixel by pixel basis, we applied Zhu et al. 2023 metallicity diagnostics to this data. And we calculated the metallicity assuming two different nitrogen scaling relations. Our results show that significant portion of the points is having supersolar metallicities. So what you can see here are histograms of metallicity measurements in AGN type regions using two different diagnostics, R1 and R2. So R1 in the top panels, R2 in the bottom panels. Then on the left, we are showing the low NH scaling. And on the right, we show high NH scaling. So what you can see is, first of all, for the same NH scaling, the two diagnostics are giving very similar results. Secondly, that in general, depending on the assumed scaling, you're having either higher or lower metallicities. However, either the majority of points or at least still a significant portion of around 20% of points are having supersolar metallicities. But what is really interesting is that when we plot these metallicities on the map, so we leverage the spatial resolution of our data, what we see is that the high metallicity regions are actually, they are creating structures. So it's not like we see just the random noise, which on average have some value and the higher points are just randomly distributed. The higher metallicity points are creating certain structures. And then we, again, leverage the fact that there are amazing quality data sets for the source. So we compared this distribution with different wavelengths. We started though with just using optical. So before that, I showed you that we calculated for each point how far away is it from the division line between Seyfert and liners. And we calculated it for each point. And what you can see is that the high metallicity is actually tracing these values. So this is the contour of this measurement slide. Then what we done is we used soft X-rays from Chandra. And again, what you can see is that these higher metallicity parts are in general co-spatial with the soft X-ray emission. And then when we look at the VLA data, the high metallicity is co-spatial with the parts in which we can see the jet lobe emission in the source. So these higher metallicities, first of all, they are creating certain structures. And second of all, they are found in the places in which we see in multiple wavelengths the AGN linked emission. So then the question is, how did these metals got there? So it could be either created just in the bicones. However, we don't see the evidence of star formation there. Or they could be transported from the nuclear regions out. So first, in that kind of scenario, we would have to have a high metallicity in the central part of the AGN. This one can be hinted by the fact that, first of all, as I mentioned before, broadline regions in quasars are showing supersolar abundances. So we can assume that we can expect that for the central part of the source for the AGN, it wouldn't be that surprising to have supersolar abundances. And second of all, recent theoretical papers and numerical papers are showing that the disk can actually self-gravitate. And there are in literature right now different papers detailing that there is a possibility of potential star formation not capturing in the disk, which could enrich the surrounding gas. Then, however, these metals would have to somehow be transported outwards. And what we've done here is we decided to put some numbers on the energetics connected to this gas which we see versus the energetic of the outflows and winds which are observed for the source. So first of all, what we done is we calculated the mass of the metal-enriched gas which we see, and we estimated it to be around 3 to 5 times 10 to the power of 5 solar masses. Second of all, in literature, the outflow velocities which have been reported for the source are up to around 1,000 kilometers per second, and with the mass rates of around 1 solar masses per year. So we just started by putting together timescales for this. So first of all, if we would assume this mass rate, in order to transfer this kind of mass, we would need around 10 to the power of 5 years. And this is comparable with the timescales needed to reach 1 kiloparsec with the velocities of around 1,000 kilometers per second. Second of all, we calculated based on the volumetric luminosity reported in the literature for the source. We calculated the mass rate of radiation-driven wind at the measured mass velocities in the literature. And we derived the 2.8 solar masses per year, which if we assume covering factor of around 0.5, again, is in sync with what has been measured for the source. So in general, both timescales and mass rates of this kind of outflows are there is no reason to say that this is not a viable scenario. And also here, I would like to point out that in literature, there have been reports of different metallicity based measurements, which also have been interpreted as potentially being carried from the nucleus out. So for instance, as I mentioned before, broadline regions are showing us supersolar metallicities. There are also papers which are showing the correlation between broadline regions metallicities and narrow line region metallicities for the same quasars. And for instance, here at Du et al. 2014, which means that at the very different spatial scales, the metallicities which were measured are very similar. We also put some numbers on the energetic of jets. So first of all, again, using the mass of metal-enriched gas which we derived, and from the literature using the outflow velocities, maximal outflow velocities measured for the source, we derived that the required power would be around 2 times 10 to the power of 41 ergs per second required to move this gas. And when it comes to radioluminosity of this, when it comes to the jet power of the source, based on the radioluminosity at 1.4 gigahertz and using the relation from Cavagano et al. 2010, we estimated that jet power can be around 4 to the 10 to the power of 41 ergs per second. So again, these are in sync, and it shows that it could be a viable scenario. And here also let me draw your attention to a very different study using very different methods and for a different type of AGN. So for instance, in Hydra A cluster central galaxy, based on Chandra data, it has been shown that the metallicity in the direction of the jet is much higher than the metallicity in surrounding intercluster medium. It has been reported by Party et al. In 2009. So similar association of the metallicity enrichment and jets has been seen previously in a very different data and for very different sources. So to sum up, we basically use the high spatial resolution data in order to map the metallicity of the Mrk 573 AGN ionization bicone regions. We combine HST data with Muse spectroscopy in order to get those measurements, and we found that the metallicity can reach up to a few times solar. We found that the distribution of these metals is following a different multi-wavelength data which are associated with AGN activity, and putting some numbers on these energy scales and time scales showed that they are comparable, so it is viable for this metallicity enrichment to be AGN-driven. When it comes to future plans, there are 7 more galaxies which have a data set which will allow to conduct this sort of analysis, so that's what we are working on right now. And if you're interested in details of this analysis, here is the link to arXiv paper detailing it, and it will soon be published. Thank you very much for your attention, and I'm happy to answer any questions.
Thank you, Dominika. This is a wonderful data set and really beautiful result. Any questions for Dominika? So if you have a question, Travis, go ahead.
Hey, thanks. I was trying to write it out, and then I just thought I'd raise my hand instead. So, hi, Dominika. So, question about your energy calculations. You said that the outflow or the amount of energy coming out of this thing is something around 10 to the 41 ergs per second. And then you note that the jet power is just roughly twice that. So would that would be then suggesting that all the energy is coming from the jets then in this situation? Because we've looked at this target a couple times before, and we've shown that photoionization and radiative driving does a pretty good job explaining the kinematics that we see here. And if you look at all of the IFU data, it's probably going to suggest that it's heckin' photoionized. So could a potential other explanation be that the amount of the energy that you're seeing in the radio is a byproduct of the winds that are running into this? So what you're doing then is you have the feedback process driving that small gas, and it runs out into those 2 arcs that you traced so well, and that's where you're getting mechanical feedback input from the outflows, and that's potentially what's giving you the radio flux that we're seeing here?
It's very possible. So what I wanted to do here is I wanted to just put the numbers of energetics. So what I'm doing here is just I compared how much power would be required in order to move this gas at this velocity, and just compared it to the jet power estimates from the radio. So by any means, I don't claim that this is what's happening. It's more just putting out there that the energetics would be unsynced. And the same is with outflows. And I agree, given this particular source, it's probably much more linked to the outflows. And in general, the emission is very photoionized driven. I agree with this point. So here, I'm not trying to say that all of this emission is driven by the jets. What I just wanted to point out is that the energetic scales are comparable. So that's what I wanted to put out there.
Okay. And then following up on that, I guess then are there any plans to do any sort of like shock analyses for the feedback that's going on here to see, I guess, is that where you're getting or maybe we could do like what kind of outflows are creating, what kind of energy is being injected, and if that's similar to the radio signal that you're seeing there, to see if that could be producing it as well. I think that'd be really interesting to come full circle then for this.
So for this source, one of my collaborators on this paper, actually Pei-Shin Zhou, is actually working on the diagnostics to basically disentangle the radiation and kinematic feedback using Muse data. So this is paper which is actually under preparation right now.
Awesome. Super cool.
That's what we are doing as one of our follow-ups. Absolutely, yes.
All right. Thank you so much.
Thank you.
Thanks, Travis. Next one we have Suhas.
Hi, nice talk. Can you go to the next slide where you were discussing about the disk?
About what? Sorry.
Yeah, correct. So like what type of like metals you got from the disk?
So this one, I believe, so here is just to point out that there are certain simulations which are showing that there can be the star formation in the disk. So this is basically numerical simulations which are showing that you have a self-gravity in the disk. Therefore, it is possible to create stars there. But this one was just out here to point out that you can expect in the nuclear regions to have high metallicities.
I mean, like there are lots of non-jetted AGNs, particularly the Seyferts. We see some outflows from at like less than 1 keV, and like basically the nitrogen lines and oxygen lines. So that we do usually with the XMM RGS spectra, that we see such outflows in those systems. Have you like found anything like that?
For this source, we haven't looked at the XMM Newton spectra, to be honest. So for now, we just looked into the images from Chandra, the images in optical, and that's how we compiled this data set. So yes, we haven't looked at this, but for sure that's worth checking, Irvine. Thank you.
All right. Let's take one more question from Mitchell. Thanks, Mitchell. Go ahead.
Hi, Dominika. Really nice talk. Nice results. So I'm jealous of your data set because when we looked at this in 2018, we just had the HST long slit. So I was just curious, I missed just how deep the Muse data were. I was curious just how far out can you trace the O3 ionized gas? We've always focused on these inner regions, the outflows, for good reason. But I was just curious, just how far out you can trace that AGN ionized gas with this data set.
Few kiloparsecs with Muse. So here it is zoom in a bit, unfortunately, because with HST data, I am unfortunately only go deep enough to see only these inner regions. With Muse data, it is around 1 kiloparsecs. This is 3 kiloparsecs in the bicone region. There are Muse data, more or less.
Very nice. Thank you.
I love the discussion that we're having, and I forgot to mention in the beginning that we are planning to keep the Zoom room open after both the talks are over for some additional time. So keep your questions coming in if you have any questions for Dominika. But for now, let's move on to the next speaker.
Thank you.
Thank you, Dominika, for a really great talk and wonderful data set. So next one we have Justin Kader, who is a postdoc at University of California, Irvine. And Justin will be talking about precessing jet. Justin, please take it away.
Thanks, Plavia. Hopefully everybody can see my browser window here. Okay, great. Yeah, so my name is Justin Kader, and today I'll be presenting some of the interesting and unexpected activity we discovered in a nearby luminous infrared galaxy using a combination of observations from James Webb, Keck, the VLA, and more. Most of this work was done at UC Irvine with Vivian Yu and our awesome collaborators who are listed here. Yeah, just before I begin, thank you to the organizers. I really appreciate this opportunity to share our findings with everybody here. Okay, so this galaxy that I'll be talking about is a member of a larger survey that we're working on. So I'll start with sort of a broad stroke summary of that survey to place things in context. And then I'll talk about the data, the IFU data, particularly in the optical. And then for the majority of the talk, I'll talk about our findings for the Galaxy VV340A. Right, so the high-level summary of MANA, which is multi-phase analyses of ULERG nuclear activity, it's basically a feedback study, AGN feedback study, using a concert of observations from multiple facilities to capture, what's becoming increasingly clear to be multi-scale, multi-phase, the multi-scale, multi-phase nature of outflows from AGN. And we're targeting local universe ULERGs where this sort of activity is more frequently found. So for my part, primarily working in the optical part of the survey, the main goal is to look at outflowing ionized gas from the nucleus all the way out to, in most cases, tens of kiloparsecs. And it involves isolating the outflowing gas from, the static ISM using BPT, diagnostics, kinematic decomposition, morphology, and then estimating outflow masses and energetics. And then finally piecing together, correlations between these outflow parameters like mass outflow rate that I just mentioned and kinetic power against the properties of the AGN. And then also exploring metals transport and CGM enrichment further down the line. Okay, so the sample of local universe ULIRGs is drawn from sort of the larger goal sample of 200 some LIRGs and ULIRGs, luminous infrared galaxies, ultraluminous infrared galaxies. So there are 32 of them from that larger parent sample. They were selected on elevated H2 bracket gamma and the near infrared, so signatures of shocked gas, possibly from outflows, feedback activity, and they should be observable from Keck or have MUSE data available if they're in the southern skies. And they should have available or planned MIRI observations. Because again, recognizing the multi-phase nature of outflows, we're combining optical IFU and mid-infrared IFU observations. So you can see from these histograms here, the goal sample is the black and our monosample are the colored bins here. We're more biased towards the high infrared luminosity. Outflows are typically more frequent in the late stage mergers, of which LIRGs and ULIRGs are usually merging systems. And so if we're selecting on outflow activity via H2 bracket gamma, we're probably going to be getting more of these luminous ones, which you see here. Otherwise, in terms of AGN fraction, IR luminosity of the AGN merger stage, we're pretty representative of the larger parent population. Okay, so just in talking about the optical data here, so we're using Keck, KCWI, our own observations, as well as MUSE observations. So the IFU spectroscopy, we have moderate spectral resolution, velocity resolutions around 80 kilometers per second, cover a wide optical range, 37 to 7200 angstrom, and we are resolving down to several hundred parsecs. In this wide optical range, we have a lot of collisionally excited lines, recombination lines, so we can do the BPD diagnostics that we need to do, nebular diagnostics, radiation field hardness. We also have the sodium 1D absorption feature from interstellar gas, so we can use that to look at the neutral outflows, just using the optical data. So just like a quick preview of what some of these data look like. This is IRES 1364, 1042. Just showing here some of the 1D spectra from this nuclear extraction. We're using the KCWI high resolution grading. So we just selected these 4 optical, band passes centered on lines of interest, which you can see labeled here. And in this case, we have an aperture on this sort of interesting dust sort of cone here, where we can see some really interesting H alpha N2 line profiles. Trying to keep track here. Okay, this is UGC 5101. This is like a disk aperture here, where we can see the emission lines are very bright and narrow, and then nuclear extraction, very deep sodium 1D absorption, some really broad emission lines here, and some deep stellar absorption as well. And then this off-axis, off-disk, excuse me, aperture, where again, we have these sort of like blue shifted line profiles. So something interesting going on here. And by virtue of this, being an IFU, KCWI, we're not going to be looking at 1D spectra all day long. We'll be mapping some of these lines across the field of these galaxies. And in this case, just looking at the O3, we already see, some tantalizing structure here. And so these spectral cubes, like I mentioned before, several hundred parsec resolution. Individual pointings from this instrument are 20 by 30 arc seconds. So, and then we mosaic around this galaxy using, 3, 4, 5, 6, sometimes up to 12 pointings to cover out to 10 to 20 kiloparsecs from nucleus. Takes about 2 hours per target to accomplish that. This is about 2/3 of the sample. This is just HST broadband, composite imaging, and I'm overlaying here the O3. This is preliminary, but you can already see there's some interesting structure in the O3 emission in a lot of these galaxies. You can see VV340 here is the one that we'll be discussing. Also mapping the neutral gas here in pink. Already seeing some interesting structure. And this is just to show that, sweeping through wavelength bins here to encode velocity information, we can do this sort of high resolution kinematics work with these data as well. Okay, so early results from the survey as a whole. Like I said, in the O3 and O2 flux maps, we're already seeing extended filaments, shells, blobs that are not coincident with stars in many cases. Just quick BPT by eye, essentially, just quick plots reveal that extended gas is, has line ratios consistent with shocks or AGN ionization. Some of the sodium 1D maps show bicone morphologies, and even the compact O3 sources show some interesting features, broad asymmetric line profiles, for example. Okay, so a summary of this MANA survey. The idea, at least for my component, my work on the survey, is to, look at these large-scale ionized outflows, that debris, and as well as the neutral gas component, and then, estimate some of the AGN properties from the KCWI data, get the black hole mass, the AGN luminosity, and then piece together these scaling relations. How does mass outflow rate compare to, AGN fraction, for example? Also bringing in the molecular outflow rates from some of our collaborators on this survey. And then looking farther into the future, doing resolved metallicities. Okay, so let's talk about this galaxy, VV340A. This is the one that we're here to talk about. Anyway, so the story here is that, Vivian had this cycle 1 James Webb proposal with several of these nearby lurgs, to be observed with the MIRI mid-infrared IFU. And as these data came in back in, starting in March 2023, they came in over a period of time. And so the team sort of divvied up the galaxies and said, okay, as soon as this data comes in for one of the ones I selected, I'm going to, hit the ground running, process the data, start the analysis, and prepare things for the survey papers we're going to write. I had selected the exclamation point here, VV340, because I thought it looked cool. And the original Goals 2009 paper, the Spitzer IRS, there was detection of neon 5 in the nucleus. So there's already some indications there's still cool stuff going on here. So I chose this. And lo and behold, it was the first target in our sample to be observed with MIRI. And what happened is when I started to look at the data, we very quickly realized this galaxy deserves its own paper. So I'll get into that. Anyway, it's got a distance of 160 megaparsecs. It's an early stage merger where this northern component, VV340A, the one we're focused on, is about 30 kiloparsecs from its neighbor. But because there's not a lot of warping in the disk of either of these, it's probably the case that in real space they're more separated, and there doesn't seem to be evidence that there's been paracenter passage yet. So this is an early stage merger. the northern galaxy is bright enough in the infrared to itself be a LIRG. It's been classified in the optical as a liner. But as I mentioned, there's a neon 5 detection in the nucleus from Spitzer IRS, and there were hard X-rays also detected with Chandra from the nucleus. So probably this is an obscured AGN. Okay, so just talking about the data that we have here, the IFU data, MIRI observed, from the nucleus out to about 3 kiloparsecs. That's the red box. And with Keck, KCWI, we mosaicked several pointings to get this blue box here, where we go out to about 20, 25 kiloparsecs from the center on the diagonal here. With comparable spatial resolution, several hundred parsecs in each case. So the first thing I looked at from the MIRI data, once I processed it all, were these line maps. So that's what you could see here. I looked at all the bright mid-infrared emission lines, and I've got them here ordered in order of increasing ionization potential. And for each row, you got the flux, velocity, and dispersion. And the first thing that caught my eye was there's this pattern in the flux maps as you look at increasingly higher ionization potential, where low ionization potential, there's a lot of emission on the star-forming disk. But as you get to higher ionization potential, you start to see this off-disk emission and bright emission from the nucleus itself until you get to these coronal lines, so ionization potential of like 100 or so or more, and there's no emission on the star-forming disk. It's very bright in the nucleus, and you have these very extended sort of filaments, collimated structures that extend right to the very edge of the MIRI field, and that have these really interesting kind of telling kinematics that you can see here, which indicated to me that these look like sort of this symmetric radial streaming motion. So looks like an outflow of coronal gas, high ionization gas that we were seeing here. And this is just another way of looking at that with these channel maps. I guess the thing let me start with just this image up here. The green is HST, a broadband optical image, and we've overlaid this velocity integrated neon 5 emission that extends to something like 3.5 kiloparsecs on either side from the nucleus. So this is very extended coronal line gas. And what's more, I mentioned before, the kinematics are very interesting. I mean, looking at these 3 1D spectra of the neon 5 line here, extracted from these 3 apertures, you can see that, in the southwest, things are very blue shifted, 500 in excess of 500 kilometers per second. And then in the northeast, also high velocities, but you see this sort of line splitting. You also see morphologically this sort of fork behavior. So these sort of started to indicate that there might be some 3-dimensional structure here. Okay. So what I had to do next, because I was very, very curious, is what do the optical data look like? So we had KCWI observations from 2022. I just mapped the O3 and I overlaid it here so that you can have a look. And what we saw is that there's this, again, very large scale, but much larger scale collimated emission of ionized gas. This time it's O3, low ionization potential. And it has the same position angle, essentially orientation, as the neon 5. So, the mystery sort of deepened here as to what is going on. What's going on with the kinematics of the O3 though? Is this just like some sort of static structure that's sort of co-rotating with the disk, or do we also see streaming motions? So we investigated that by comparing the in this case O2, but we did it with O3 as well, velocity field with a bulge disk halo dynamical model, rotation model of this galaxy. And we did that in 2 synthetic slits. There's like this disk slit here. And that you can see in panel E here. The heat map is just the actual O2 velocities along the disk. And they're very well fit by these green squares, which are from the dynamical model. So it seems that, that it's pretty clear that the O3 is just rotating like a disk along the disk, but along these filaments here, which is this sort of tilted synthetic slit, the rotation model does not do a good job reproducing what we were seeing in the O2 and O3 velocities. So you see these sort of like forbidden velocities here, very high dispersion. So the idea here is that we have these streaming radial motions coming not just from the neon 5 coronal lines, but also from the very extended O3. Okay. And then throwing into the mix the VLA data. So we were showing our colleagues what I just showed you in some meetings, and Loretto raised her hand and said, well, we have some VLA 6 gigahertz radio continuum training. I seem to recall it looked interesting. So why don't you take it? I'll clean it up for you and overlay it and see what happens. And that was very auspicious because when I did that, we got this, which was just like pretty jaw-dropping. So we have very bright continuum emission on the star-forming disk, but what was striking was this off-axis synchrotron emission seems to trace an S-shaped jet. And the linear part of this jet does also align really nicely with the collimated outflow that we're seeing. Okay, so what's the deal with these S-shaped jets? They're similar to predictions of helical precessing jets driven by a wobbling accretion disk. You see some example simulation output here and a cartoon here. Just checking the time. Okay. So the idea here was, okay, is there a way that we can model, the precession period of this thing? What's the geometry of this precessing jet? Let's see if we can constrain those things. So the way we did it was by, adopting a ballistic helical precessing jet model. Ballistic as the ejecta travels along the jet, it just goes in straight line trajectories. Helical because it's got that wobbling precessing pattern. And, essentially taking the parameters for that precessing jet. So what's the precession period, inclination, precession angle, so like the opening angle of this precession, position angle, varying those parameters, getting the 3D model, and then each time projecting that into a 2D synthetic image and comparing it to the real VLA data, 6 gigahertz data. So the real data is on the left here. I'm just masking out the disk, and then contours. And then on the right is our best fitting model with the real data contours overlaid. So we seem to be able to find a pretty good fit. And then when you let the model run for several precession periods and overlay it as these green sort of traces, what you see is that they fall on top of this very extended O3, at least at the edge of this sort of precession cone in the southwest. And then in the northeast, you also have this sort of faint blob of O3. So it looks like there's some sort of connection here. And we didn't use the O3 in any way to do this fitting. This is just from the VLA data. Okay, so putting this all together, what's the physical interpretation and that we came up with? And it was that this is a jet-driven outflow based on the morphological alignment between the jet and the outflowing gas. And so what's the physical model of what's going on here? So the idea is that the jet is pushing ambient material in the disk outward along these ballistic trajectories. And then over many precession periods, outflowing gas forms this sort of hollow bicone structure. I'm illustrating that here with this video I found. This is actually an X-ray binary, hence the tiny, tiny scales. But it's the same idea. Okay, let me go to the next slide here. Okay, so how did we, measure these velocities? How did we get the mass outflow rate? All of that. So we assumed a velocity law where the material is linearly accelerating along the bicone walls until it hits a turnover radius, after which point the ejecta begins to decelerate. Again, all along the walls of this hollow bicone, and driven by, the plasma from this jet coupling to the ISM and pushing it. So that's the velocity law for this model. And then the bicone itself, the geometry is fixed to the precessing jet parameters. And we find that a model with a turnover radius of 1.25 kiloparsecs and a maximum velocity of 1,200 kilometers per second does a pretty good job of fitting simultaneously the O3 velocity data and the neon 5 data here. So panels D and E are just position velocity data along this diagonal slit that follows these extended, collimated outflows. And whereas, again, the dynamical model just in the green here does not produce the velocities that we see in the O3, this bicone model data, these blue circles that come from panel B here, just the model PV data along this blue slit does reproduce these sort of forbidden velocities. And then again, for the neon 5, just taking that same model and doing a smaller synthetic slit and getting the blue points to plotting those results over the neon 5 velocities, we see it does a good job. And even reproduces this line splitting that we see in the northeast due to the hollow nature of the cone. Okay, so we find that the outflow, so from an energetic standpoint, is it plausible that the jet is able to do this? So the outflow kinetic power, 10 to the 43 ergs per second. The jet kinetic power from 1.5 gigahertz imaging, and using the same calibration that was mentioned in the last talk, the jet power is 4 times the outflow kinetic power. So that ratio of a quarter is within the range found in simulations of radiomechanical feedback, and it's seen in distant radio loud ellipticals. It is at the high end, though. We think it's due to the fact that this jet is moving very slowly, and it's able to very efficiently couple with the ISM and deposit much of its energy in driving this outflow. Okay, just a couple additional curiosities. We looked at the ALMA data, and we don't see any cold molecular gas in the outflow at all. So there does not appear to be a cold molecular component to the outflow, which is curious. Could be that the jet is destroying molecules, dissociating them. And then another thing is that if you do a very strong stretch of the O3 data, you see these blobs in this sort of orthogonal direction. These precession jet models do show ejecta can occur along the orthogonal axis, or there could have been a reorientation event where the precession axis flipped some time ago, constrained it to be more than 3 mega years ago because of our precession period and the fitting to the O3. And then the last thing I would mention is that we did find a tentative detection of extended emission at high blue shifted velocities using H2 emission from James Webb, but this is tentative. It's very low signal to noise. So the conclusion is that, we have a disk galaxy here in an early stage of a merger, but it's exhibiting this very odd feedback behavior where it has this jet, albeit low power, that seems to be wobbling, first of all, and then it's driving this large scale outflow, which has a mass outflow rate of 19 solar masses per year. It's about a quarter of the star formation rate. It's not quenching the galaxy, but it's significantly altering the future of star formation here. And yeah, we think that's very cool. So if you want to read the full paper, it was in last month's February 26th issue of Science. And what was very cool to us is that they actually put us on the cover, which was surprising and very fun. Yeah, so that's it. I'll end it there, and thanks very much.
Thank you so much, Justin. This is a really cool poster on the Science magazine, and the talk was really amazing as well.
Thanks.
I know we are top of the hour, but we would like to continue discussing. So if you can stick around, please do. And if you have any questions for Justin, and once that's done, we'll come back and ask the questions for both speakers. So if you have any questions for Justin, please. Feel free to raise your hand or type it in the chat. Travis?
Hey, Justin, thank you very much for your presentation today. So the O3 structure that you're seeing out there looks really linear. Whereas you're seeing that the radio structure in this has that really beautiful S-shaped. So if you're presuming that the radio, if this was a jet, is normal to the accretion disk and to the torus in this situation, then you would kind of presume that the whole flashlight of doom then potentially is also wobbling. And so why don't we see the O3 if this was the situation? It doesn't really follow like I guess what would be the earlier part of this precession, like the curviest part of the radio structure. So where would the O3 gas be in that situation, versus the linear shape that you're seeing?
Yeah, this is a great question. So I my answer is that under, let's say, different circumstances, you should expect this O3 gas, this very extended O3 gas, to just follow the shape of this precession cone. And it's not what we're seeing. It's as if the gas is only following one edge of this theoretical bicone wall. And my answer to that is, that it could be you get this from, when the jet has uh, when it's oriented through the most disk, that's when it's able to couple to the most material and drive it outward. And so that is what you see. I mean, if alternatively, the gas was preferentially on this other wall here, these are the lines of sight, or I guess that you could call it the trajectories where it actually goes through the minimal amount of disk material. And, so it wouldn't really make sense. I think our answer is that, you're preferentially getting this linear structure because, those are the times when the jet is moving through the most disk and pushing it outward. I mean, with a very strong stretch, you might convince yourself that there's some O3 here, and these are, I can't quote the signal to noise of these lines out here, but by eye, I mean, they're clearly there. So yeah, that's my short answer. I mean, you also mentioned that the flashlight of doom, maybe you're referring to like the ionization cone.
Right.
Yeah, I mean, I, I'm not considering an ionization cone. I'm just thinking about this linear jet that happens to be wobbling.
I see.
And yeah.
So then to follow up on that, so we looked at a nearby AGN, a liar, LLAGN, whatever you want to call it, NGC 4258, where we look at, it also has this really beautiful like radio structure that's going on there. And so when we were looking at it with Webb, we were seeing faint shock structures that were following along that and it worked pretty well as an explanation of it being like a feedback, a shock process going on versus necessarily a jet. Did you guys do any sort of checking back of the envelope calculations to see if that would potentially be what's going on here?
Um, so in other words, are you saying like that this, yeah, maybe.
So in this scenario, it seemed it potentially could be if it's a similar scenario is where you had the feedback going out and then it splashes into that host material and then kind of comes up, kind of like the Ariel on the rock with the little mermaid splashing the water up behind her. So it creates like those splash, and so that's running into that material above the plane and shocking it, kind of creating that S-shaped structure
Ah, gotcha.
potentially.
Yes, 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 yes. Okay, so, um, yeah, we definitely considered this scenario. In other, maybe you can tell me if it's not fair to characterize what you're saying in this way, but essentially that, as this, instead of precession, what's going on is you have a linear jet, and when it essentially encounters some material, it sort of deflects, and so this shape that you get is not the result of precession. Instead, it's that like this jet comes out and it hits some dense medium and it sort of deflects there. And I think that our response to that is that there's such clear symmetry in the S shape that it seems like harder to explain using that scenario unless the dense medium is exactly the same you know disk height from the nucleus. Um, yeah, I think that's my answer to that one.
Okay, thanks so much.
Yeah.
Any other questions? Kristen? While people are thinking, maybe I can ask one question, Justin. This is a really cool modeling that you did. I missed your point about what could be causing the orthogonal outflow. Can you explain that again?
Oh, you
The
mean
O3.
yeah, I'll go back. Yeah, you mean essentially,
This
let
one.
me minimize this. Yeah. This oops. This stuff here and here.
That's right.
Um yeah, the idea is, well, where is this coming from? I mean, you have this collimated, large scale O3 filaments in one direction. It seems to be aligned with the jet and with the inner neon 5 stuff. So what's going on with this also pretty extended O3 in the other direction? I mean, the model that we're presenting doesn't directly predict this stuff out here. One thing I'll say is that we did do O3H beta mapping of this source. Didn't have the H alpha at the time. And while we did find, shock-like or AGN-like very high O3H beta ratios along this main direction of the outflow, in these orthogonal directions, we found relatively low O3H beta. So there might be something fundamentally different going on here. And that's one piece. The other piece is, you know, well, I guess that's the main piece. The interpretation would be, our primary thing is that this is not a good image to really indicate this. There's a third idea that I didn't really mention. I mentioned reorientation of this whole thing, right, where it just flipped and a long time ago, where originally it was oriented in this direction, and you have this ejecta, here and here, and then it flipped and you have it here now. So that's one idea. The other idea is that even if it never did flip, you just have this static precession axis in this direction. Simulations do show that you can get, ejecta in the orthogonal direction to the precession. So that could be what's going on. And the third thing that I didn't mention, if you look at H alpha imaging from HST, this southeastern blob here looks, qualitatively different than the other features. It has these sort of like arcs and shells. So it may be some sort of smaller scale, galactic fountain thing going on, driven by supernovae and the disk. It seems like, these structures sort of erupt orthogonally to the disk at that location. So that's just another idea. Hopefully that clarifies what I was saying there.
One thing that was floating in my head was maybe could it be a restarted jet activity as well? So, and is there a way of knowing if there was a prior epoch or something that pushed this gas out?
Yeah,
It's
I think it's an open question, but it's very cool. I mean, one of the things that I really would like would be much deeper radio continuum imaging of this source. Do we see the synchrotron, more synchrotron aged material, but nonetheless radio emission following our model? Do we see maybe some old radio emission in this orthogonal direction, which would show that, maybe there's like reorientation, restarted jet? You see gaps in the O3 here too. You have very strong O3 emission. There's a gap here and then more here. I mean, maybe it's like a sputtering jet. And that's, it's pushing out stuff while it's on and it's not pushing out stuff when it's off.
yeah.
Yeah. Thanks for the question.
pretty cool. Yeah.
Yep.
So I want to open up the floor for both speakers. If you have any questions for both either Dominika or Justin, or just yeah, just feel free to either raise your hand or unmute, and then I can ask you to unmute, or you can type it in your chat as well. I do see there's one question by Suas in the chat. Is there something, Suas, you would like to follow up on right now? Or if Dominika, you have an answer for that question.
Yeah, I think it would be very interesting to look at. We haven't looked in the different data, spectral data, but I agree it could be potentially very interesting to look at.
Awesome.
I actually have a quick question, Dominika. You showed your sort of metallicity maps, and it showed, enhanced metallicity on sort of these like inward facing surfaces. And then you overlaid contours. I might have missed it. Were those X-ray or radio contours?
Both of them. So we
Both.
have
Okay.
like 6 centimeters and soft X-ray from Chandra. And yes, so that's what they trace.
So you like described that they seemed, in both cases to trace these, enhanced metallicity regions. I'm just wondering, like, what's the idea there? Like, why would you expect that to be the case?
I mean, that's the open question, right? Like in the sense that we were thinking about different ideas how you can get these metals out there. So, we just, throw out different ideas, and one of them, okay, like what if this is just the outflow of the material, which is more metal rich from the vicinities of the nuclear regions. And so therefore, first of all, you have those outflows, and in the parts of the source in which you can see much more, AGN-driven activity, those are also the parts in which you see those enriched metals. The other idea which we are floating around there, the one in which we connect kind of jet, is that there are also papers which are showing like a dusty outflows. They're pretty recent papers from JWST. And so the other idea, which we just wanted to out there, okay, like maybe what you see is that in these parts in which you have higher activity, you are destroying the dust grains, which also can be just metal rich, and you are putting them in the phase in which they actually can, can generate the null lines. So we just, that was kind of our thinking, but I don't have a definite answer, right? It's difficult to say it just from the sponsors.
Yeah, that's really cool. I mean, look at the X-rays. It's like, it makes you wonder if this stuff is being like violently deposited, and there's maybe shocks or something.
It's a good, that's our tool, let's say, ideas of how it can be.
Yeah, it's really cool.
Travis is saying that shocks free up the iron, right?
So the iron, in Muse data, so there are 2 exposures of Muse for the source. One of them is shorter, one of them is longer. Unfortunately, the longer one has much worse sync. So we were working on the shorter one, and in the shorter exposure, we don't see iron 10 or iron 7. If that's what...
Oh, you can. I went and downloaded it once you start showing it. It was so cool. But you can see the iron 7. It looks pretty much like the X-ray that you were showing. So
in the longer exposure, I guess that's
yeah.
nice.
Any other questions?
Can I ask one kind of broad question of both of our speakers? We've been focusing a lot on preparations for Astro 2030 and thinking about what we'll need in the future. So I just wanted to throw out the question to both of you. take the next big steps in the science questions that you're asking, what either existing or potentially future facilities would you want to see made available to be able to enable you to take those next big steps? So I'm totally putting you on the spot, so it's okay if you haven't thought this through at all, and I don't have an answer ready, but we'd be really curious to hear what your thoughts are on that.
Was that a question to the two speakers? Yeah.
Yes.
I want like a far infrared observatory. I think doing, rest frame mid infrared farther out be really, really interesting. I'm interested in these coronal lines that are in the mid infrared. But like with an older population of obscured AGN, are there fundamental differences between what's going on at higher redshift compared to these nearby universe ULIRGs? I'm also interested in, rest frame far infrared too, like the C2 line and star formation, calibrations and things like that. I think there's a whole lot to be understood using these, far infrared forbidden lines when it comes to, embedded early, star formation.
I mean, from my point of view, I usually so my background is mostly in X-rays. So what I do right now is I try to connect different multi-wavelengths, and I find it's very interesting how different things can be seen from the different perspectives. And so I would say in the longer term, what is very scary for me is the idea that we won't have a good spatial resolution in X-rays, because there are a lot of processes which, seeing the X-ray extended emission can tell you a lot about what you actually see. And it's much more difficult to do it based on different wavelengths. So, I would put more this twist on from my point of view and from the point of view of my research.
Yeah, no, that's really cool. The really missing point is X-ray, a great X-ray and a far infrared observatory. So I hope our next flagship missions or any missions are focusing on those. I'm happy. I mean, if there are no questions, we can end on a big note here with looking into future. Unless people have any questions, going once, twice. Okay. If not, Justin and Dominika, really, really thank you for staying longer and answering all the questions.
And thank you for all of the questions. And
It was
really
fun. Yeah, it was really fun having
Been fun.
you.
Thank you.
Thank you so much. Bye-bye.
Bye, everybody.